Okay, so let's review where we are. A lot of build-up there talking about block ciphers. So just as a quick review, we established the syntax for a block cipher. It's a mapping that takes in a string that we call a key, which has some key length k, and another string which has length n, which we call the block size, and it outputs a string that has also the same block size n, where these k and n are some integers that are at least 0. And we've said that a block cipher, well, a mapping like so is a block cipher if and only if for every key k, this mapping e sub k is a permutation. And here we're using the function family representation of this two-input function. And we also established some notation. The set perm n is the set of all permutations. Usually in class we'll use the Greek letter pi to denote permutations. So those are, again, one-to-one onto functions, not the number pi. So perm n is the set of all permutations over bit strings of length n. And then BC, standing for block ciphers, KN, that's a lowercase k, by the way. I realize it looks a little tall. This k and this k are the same. This is the set of all block ciphers that have k-bit keys and n-bit block size. So, right, so there we are. And so we've got all this syntax in hand now. And the next question that we'd like to ask is, well, okay, if I have this object at my disposal, from a cryptographic perspective, what kinds of things would I like it to be able to do? I mean, I know that functionally it gives me an invertible, mapping for every key. By the way, you might pause and ask yourself, why is it that we want a block cipher to be invertible in the first place? And if you think about that for just a second, when you think about encrypting things, so let's say that, let's say you're using like the CBC mode or the ECB mode from the previous portion of this lecture, and you've got plain text blocks that are going through. In fact, let me see if I have do I still have the picture? Yeah. So we've got, here is AES, it's a block cipher, and why do we need it to be invertible? Well, if you look at this, if you take your plain text block and you bitwise exclusive OR with the IV, and you run it forwards through, so AES here is our E, the key here is our K. If you run it forwards, you get a ciphertext block. Well, now imagine that you're on the receiving side and you're in possession of the same key, and you'd like to now decrypt this ciphertext block. Well, then you have to be able to go backwards through this to get to this point. And then if you have also the IV, you'll be able to then bitwise exclusive OR this wire with this wire to get this. And because XOR itself is invertible, you'll get back the right plaintext. So to do decryption, we needed the ability to invert this. So that's why block ciphers need to be invertible. We'll see, in fact, that there are some encryption schemes that use block ciphers that don't actually need the block cipher to be invertible. Those are kind of cute. For example, counter mode is one of these. In any case, that's why we want for block ciphers to be invertible. And so yeah, there we go. Okay, so functionally we know what a block cipher is supposed to look like from the outside. It has these two inputs, it has an output. These are the same size, and we know that it's supposed to be a permutation for every key. But from a security perspective, what do we want block ciphers to give us? What would it mean? So this is really the question we want to answer now. And we'll take a few stabs at it before we finally get to the definition that we want. So the question is, what does it mean for a block cipher to be secure? Well, there are lots of things. I mean, maybe you can just sit and think about that for a second, because really what we're about to do, answering this question in a formal way, it really is the heart of what this class is about. Trying to take this fuzzy concept of secure and applying it to an object that we now have some syntactic understanding of, a block cipher. Now we're taking the step of saying, okay, what I need a way to actually measure security of this object called the block cipher. And I think, I think probably maybe like halfway through the class or so, you'll really appreciate all this definitional work that we're going to do now and throughout the course. That I really can't stress this enough, and I'll continue to stress it throughout the class, that the kind of definitional things that we're about to do, they're really hard. They're very hard to do, and it's very common that these security definitions are sort of living, breathing things that change over time as we come to understand them better. But really, the reason that's hard is because we're asking, what does it mean for a block cipher to be secure? You have to start thinking about, well, secure with respect to what? Is this an application-dependent question? What kinds of attackers do I need it to be secure against? What sorts of goals might the attackers be trying to fulfill? What sorts of computational powers do attackers have? All those sorts of things are rolled into this question of what does it mean to be secure. So let's start with what I think is a somewhat obvious and natural hardness property. So security, you can also think of this as being a hardness property. I'd like to know a hardness property. So here's sort of a natural hardness property, I think. I'm going to write this in yellow. If you think about, let me pull this picture back up again. If you think about this picture of CBC mode encryption using this block cipher, you can be sure that if by seeing the outputs just of this one block cipher here, let's say that you could see, that you could ask plain texts just block at a time, and you could see the resulting ciphertext that come out. If you could recover the key, if you could guess what the key is by seeing some input-output pairs for this block cipher, then the game is whatever security you think you're getting out of this CBC mode encryption scheme, you're no longer going to get, right? Because we established in the opening lecture that the only thing that we try to keep secret in an encryption scheme, in fact in any cryptographic object, is the key, right? The adversary is going to know, oh, AES is being used, and it's being used in CBC mode because that's the algorithm for doing encryption in this picture. The thing it doesn't know is the key. So for sure, if the attacker, or the adversary as we'll typically call it, can guess the key easily by seeing a few plain text ciphertext pairs coming through this block cipher, then all hope is lost, because now the adversary has the key and there are no more secrets anymore. So the adversary can do everything that the honest parties can do. So I think that's a natural first place to start, is to think about it should be hard to recover the key. This is a typical sort of thing that people would say. It should be hard to recover the block cipher's secret key. Okay, so good. We have a candidate security property in mind, namely that we want to keep the secret key secret. The next question is, what does it mean for hard? Hard with respect to what? Like in the example I just gave, I said, well, if you see some plaintext ciphertext pairs, you shouldn't be able to guess what the secret key is. But you can always guess what the secret key is, right? So let's think about this for a second. If I have a key, let's say that K, say that K is equal to 128. So the key length is 128. Then what's the probability of just guessing, like before you even interact at all with the block cipher, seeing any plain text ciphertext pairs? What's the probability of guessing the key? Well, if you guess, let's say that the key is picked uniformly from the set. So the secret key for the block cipher is just a uniform random sample from the set of 100 of bit strings of length 128, then so if the key k is uniform, (0, 1 to 128), then what? The probability of guessing the key just without doing anything is, of course, 2 to the minus 128. Right, so this is just intuitively obvious. If I pick a key uniformly random, and I just say, guess what the key is, then the probability that you can guess what the key is without doing any work at all is always at least 2 to the minus 128, because that's just the probability of you guessing each of the 128 bits individually. So that's fine. There's always some chance that you'll guess, but of course this number is astronomically small. Sort of a weird turn of phrase, astronomically small. It's infinitesimally small, so you're never going to get the key, like this. So then the question is, okay, well, that's hard for sure, but this attacker that we sort of implicitly described is kind of a dumb attacker, right? It gets told, okay, I picked a key. What is it? And the attacker just says, oh, well, it's 0, 1, 1, 0, 0, 1, 1, so on. So it's hard against that attacker, but we want hardness against real kinds of attackers. So we're going to consider situations. Let me scroll up a bit here. Good. Let's consider attacks in which the attacker actually gets to see some plain text ciphertext pairs. So let's consider attacks in which the adversary gets to see plain text ciphertext pairs. In other words, inputs and outputs of the block cipher. So we're considering adversaries that can see potentially many plaintext ciphertext pairs, and this is a shorthand, PTXT for plaintext and CTXT for ciphertext. Okay, many plaintext ciphertext pairs. Well, there are more than just there's more than just this input for the block cipher, right? There are 2 inputs for a block cipher, and there's key as well. So we have to address where that key is coming from. So this shouldn't be a period here. Let's say this is under a uniformly random secret key. Okay. Now we're getting closer. So we're considering attackers. This is getting closer to a real situation. We have a secret key K that has been picked uniformly at random. So we've got a uniform string of k bits that's acting as the key for the block cipher, and the adversary is going to be able to see potentially many plaintext ciphertext pairs. And well, we've said that the goal is the adversary is trying to recover the key. So this is sort of the attack. This is the attack scenario. Maybe I'll write this in magenta. This is the attack model. And then the goal is the adversary wants to guess the key with probability that's better than just being able to guess it uniformly, or just guessing the uniform key. The adversary wants to recover the key, and this we can think of as being the adversarial goal. Okay, so we're getting closer now to having actually a real security notion for block cipher. We've got an attack model, so the adversary is getting to see plaintext ciphertext pairs under a uniformly random secret key K, and it wants to recover the key. So to help us visualize these things, let's draw a picture, and we'll do this kind of picture drawing often in the course. It's helpful to sort of visualize what's happening before you start writing down the formal pseudocode experiment that underlies the security notion. So here is the idea. Let's draw our adversary A in red because adversaries are bad. So here's our adversary A. And we've said that the adversary is getting to see potentially many plaintext ciphertext pairs under a uniformly random secret key K under the block cipher. So what we're going to do is we're going to provide the adversary with a black box. And this black box is going to give, let's just put the box here. So here's our box. And the adversary is given access to a black box whose functionality is E sub k, where, write this in yellow, where k, okay, here's some new notation, where k, this is the assignment operator, but if I put a $sign over the top of it, so that's a $sign. K is sampled, and I didn't realize that's going to start going so diagonal. Let me read this for you. This says, so this is the assignment operator we had before. Now we put a $sign over it. This means to sample from the set that's on the right-hand side and assign the resulting value to K. So this is a sample and assign instead of just a straight assignment. And so maybe it's worth saying a word about this. When the thing on the right-hand side of the sample and assign operation is a set, then unless we explicitly say otherwise, the sampling is assumed to be uniform. So every set in this class will be assumed to be equipped with some kind of a distribution. And sometimes those distributions will be quite complicated, and we'll have reason to talk about that in a little bit. But typically, when we're doing things like sampling keys, say, we just sample uniformly. So if we don't say what the distribution is for doing this sampling, then the distribution is assumed to be uniform. And this will become second nature to you. You'll just say, okay, I'm sampling a key uniformly from the key set. So that's the K that's in here. It's been picked uniformly at random. And we should maybe even put in here that this is done before A begins to see input-output pairs. Let me just write at the beginning. Okay. All right, so the adversary now, what's it going to do? Well, we said the adversary is allowed to see plaintext ciphertext pairs under the block cipher with this secret key K that's been uniformly sampled. And so we draw the picture like this. The adversary asks what we call queries. So it queries this black box. So think about this as like, you know, it's you as the adversary. You're sitting at your command line and you're able to, you have a program that's running, and the program is implementing the block cipher E under some secret key K, and you type in some value X. Now notice this value X, we will assume that when adversaries, you in this case, ask queries, when you type things in that are going to be run by this black box program, you don't type in gibberish things. So if you've been told that the block cipher, let's scroll up here, if you've been told that the block cipher has, it only takes inputs that are n-bit strings, and if you want to be concrete, you can say n is like 128. If you've been told block cipher that you're about to attack takes 128-bit strings as plaintext blocks, then you're not going to input a 5-bit string. Right? You're not going to input a 1000-bit string because that's syntactically not a proper input for this box, and you can just assume that the box just borks on that. So we're assuming that when you ask a query to this box, that you're not wasting time. You don't waste precious resources by asking an X that falls outside of the domain of this thing. So you ask an x, and the program faithfully returns to you a value y. This value y is in fact equal to e sub k of the x that you just asked. Well, okay, this picture is doing something slightly more than what we said up here, right? We said we consider adversaries that can see, right? They can see potentially many plaintext ciphertext pairs. This is actually giving the attacker more power. This is saying the adversary gets to choose the plaintext and see the resulting ciphertext. So this kind of attack here, because you're getting to choose X, this is called a chosen plaintext attack. Chosen plaintext attack, and typically this just gets shortened to CPA. So this adversary is mounting a chosen plaintext attack on this black box. Now, we have a special terminology in cryptography, which is pretty much just adopted from theoretical computer science, which is from where cryptography got its start anyway. This box here, we don't call it a black box. Typically, we'll call this an oracle. In particular, in this case, it's an oracle for the function e sub k. We'll see in later definitions where oracles do all kinds of funky things, but whenever we have this kind of a box here, we call it an oracle. And this goes back to definitions of Turing machines that are provided oracles. These are just tapes attached to the Turing machine, where the Turing machine can write something out on an oracle tape and it gets a response in unit time back on the tape. But you can also just think of this as an oracle as being like some box in the sky that always gives you the answer that it's supposed to give you. So you've got this oracle, and you can say, oh, oracle, please tell me what is the value, what's the resulting ciphertext that I'll get back if I ask you X, and you get the response back. So this is referred to as an oracle query, an oracle query. And this is the response from the oracle. Okay, so let's see. Okay, we've allowed the adversary to ask a plaintext, a chosen plaintext, to its oracle, and it gets back the response, which is e sub k of x. And we've said that the adversary wants to recover the key. So what does the adversary do at the end of its execution? Well, we usually write in these kinds of pictures this sort of heavy arrow as the adversary outputting something. What's it want to do in this game? It wants to recover this key. But we don't know if it can recover exactly the key, so let's give it a different name. Let's say it outputs some value k prime, and you can think of k prime as being the adversary's guess. Adversary's guess at the key. Right, that's what k prime is. And so, fine, the adversary will win the game if it does what? Well, its goal was to recover the key. So the adversary wins in this attack if, in fact, k prime equals k. So that's the winning condition. So maybe let's write this off to the side. So the adversary wins if k prime equals k. Okay, well, ta-da! This is your very first picture of a security notion. So let's step through the experiment once again. It's not quite complete yet, but it's pretty close. So what have we got? At the beginning of this experiment, we had some key was picked from the set of keys for the block cipher, and put into this oracle box was the block cipher under that key k. Then we have an adversary A that runs. It's given access to this oracle. The kind of attack this adversary mounts is a chosen plaintext attack, where it's asking query. It asks a query X, which is its choice of plaintext, to the oracle, and the oracle responds for the value y, and then the adversary outputs a guess k prime at the key, and it wins this game. We can call it maybe the key recovery game if the adversary correctly guesses the key, right? If k prime equals k. Well, there's a couple more things to do here. It's quite close, but you'll notice that that we haven't said, well, we've only drawn in this picture that the adversary asks one query to its oracle. So, we said above that if the adversary were to ask no queries and simply just output a guess at the key, then the probability that it wins this game is 1 over the size of the key set. So what happens if we allow the adversary to ask more queries? Well, we can sort of take this to the other extreme. Right? We've said if there are no queries, then it can always guess the key with probability at least 1 over the size of the key set. On the other extreme, what if we allowed the adversary to ask, an exponential number of queries? So not just one, but lots and lots of queries. In fact, let's say that we allow it to ask 2 to the n queries, where n is the size of the block cipher. Well, if we allowed it to ask 2 to the n queries, then what's a strategy for doing that? It asks first the all zeros query, and it gets back the response, and it writes down the result. And then it asks the query that corresponds to all 00001, it gets the response. And then the next one in line, it just does all of the input values in lexicographic order. If it were allowed to do that, if it were allowed to ask all 2 to the n of those queries, it would be able to write down the entire table that describes this thing. Yeah? Okay, does that make its life easier in guessing the key? One would certainly assume so, because it now knows the entire table for this. So one would expect that that a clever adversary who is allowed to ask many queries to this box should be able to win this game with probability better than an adversary that asks no queries and simply guesses what the key is. That's just intuitively obvious. So, let's augment this picture just a little bit, because there isn't just one query. There are bunches of queries. Potentially, right? We said it can see. So in fact, maybe even we'll just cross out the word see here. Not see, but choose. Choose. Potentially many plain texts. Well, it's really choosing the plain text, right? It's not choosing the ciphertext, but these are chosen plain text pairs. And we said potentially many of them. So we can think about these as, it's not just x1, but there's lots of them. There's, x1, let's see if I can squeeze this in here. x1 produces a value y1, which is e sub k of x1. Okay, so the adversary has asked a first query. And we're saying now it's going to ask many of them. So there's going to be some, x2, so maybe I'll add this, x2, and of course it's not going to be in reverse order. It asks an x2 and it gets back a y2, or y2 is equal to, oops, okay, what have I done? There we go. Y2 is equal to e sub k of x2, and so on. I don't want you to think that this is an infinite list. There's some upper end on this. Maybe we'll call like x sub q. Q is pretty common to use for the number of queries that are asked. So this is an x sub q. So it's asking q queries, and it's getting back the corresponding q responses. So yq is, man, I cannot make a decent equals sign today on this template. Yq is e sub k of xq. All right. So now we have an adversary that's being allowed to choose q inputs to its oracle, q oracle queries, and to see the responses. And after it sees those responses, it guesses what the key is. And we've just said, well, if Q is in fact 0, then we know what this probability is going to be. If Q is 2 to the n, we expect it to be something much closer to 1. But for intermediate values of Q, what we'd really like is to be able to say, okay, I don't know what Q is, but I expect that as Q grows, the probability of winning this game goes up, and I'd like to be able to perhaps be able to write down a bound on the probability, an upper bound on the probability that an adversary wins this game, given a certain amount of oracle queries Q. But I haven't said anything yet about what the strategy of this attacker is. And in fact, we never will. Unless we're giving, never will is too strong. Only when we're describing explicitly concrete attacks on objects, only then will we spell out what an attacker does. And we'll have an example of this a little bit later. But usually what we will do, particularly when we're giving security proofs or security upper bounds, these being bounds on how well an attacker can do given a certain number of queries, when we're doing these sorts of things, we won't make any assumptions about what the attacker is actually doing in order to determine what these queries should be, or in order to determine what this output should be. We want to treat attackers, whenever possible, as just some arbitrary algorithm that's running. We don't know what it does. We just know that it's going to ask some number of queries, and at the end of it, we know it's going to output a guess at the key. How does it decide what this first x1 should be? Well, this is an algorithm, so there's some algorithm that determines what this first x1 should be. Now, maybe it's even just worth saying here that adversaries, we haven't said this yet, so maybe I'll put this in magenta so it's less confusing. Adversaries are randomized algorithms. So what do we mean by that? We mean that adversaries are algorithms, and so that means that they can they run on some model of computation, which we typically just assume is just the sort of Turing machine with random access memory. It doesn't actually matter what the model is. It's just that A is some algorithm that you can write down, and algorithms, unless we see otherwise, are randomized, which means they get to flip coins internally. If you want to learn lots about randomized algorithms, you can take one of my other classes, CS 480, 580. But yeah, so adversaries can run, and when they run, they can flip coins to decide what they should do next. So maybe this adversary runs, and to choose this first x1, it just flips a fair coin 128 times, if this is a 128-bit block size block cipher, and it takes the resulting values that it gets and writes them down as a bit string, and that's the value of x1 that it asks. So it just picks a uniformly random string x1, it asks and gets the response back. Now, we want to give the adversaries power whenever we can, as much power as is reasonable, because if we can argue that this game is hard to win, even when the adversary is very powerful, then we've said something quite strong about the security of this block cipher when somebody is trying to recover the key. So when we are making positive security statements, we like to let the adversary be as strong as possible. So how does the adversary decide what x2 could be? Well, who knows? Maybe it just flips more coins to decide what x2 could be. A smarter way to approach the problem might be to say, okay, I've seen what the output is when I asked x1, and it's this y1. Okay, so now let me think. Let me do some computations off to the side, and as a result of those computations, maybe it's got some lookup table inside that says, oh, okay, I know what a bunch of input-output pairs are. Let's say that for the value x1 being the all zeros string. The adversary has pre-computed in a lookup table, so it's actually part of its code. It's pre-computed for some number of keys k, what the outputs would be on input all zeros, right? So such an adversary, if it had asked all zeros here and gets the response, it should actually just look at its lookup table to see if any of the keys that it has already thought about actually would explain this input-output pair. That's a smart thing to do, right? So if it does, then maybe its algorithm branches and tells it, okay, then I should ask particular query x2 to help me make sure that the key that I've found in my lookup table does in fact match, because then I should get back a particular y2 for that. If it doesn't match, then it takes a different branch. It says, well, I actually still don't know anything about what the key is, so let me do something different for x2. Yeah. So what that example is highlighting is the fact that this kind of attack is adaptive. So this is a word that we'll use quite a bit. Let me also write this in. Are not just randomized algorithms, but we typically think of these things, I can't find a place to fit it in. They're not just randomized algorithms, they are adaptive. I'll just write it below. Adaptive. So adaptive with respect to the input and the output that they see. Okay, so we've got this adversary A. We've hooked it up to this oracle. It's allowed to ask a query. It gets back a response. It can adapt its next query. It can adapt its computational behavior based on the value that it saw. It asks some next query. It gets back the y2. It adapts again, asks the x3, and so on, until it's asked all the queries that it wants to ask, of which there are a queue, and sees all the responses. And as a result of all that, maybe does some more computation on the side and outputs its guess at the key k prime. And we say the adversary wins if k equals k prime. This is a fully quantified security experiment. So let's go ahead and give this thing a name. Let's call this the key recovery. Key recovery experiment, or key recovery notion. Boom. This picture here describes a security notion that we're going to call the key recovery notion. Drawing these kinds of pictures is super helpful when you're trying to sort out what a security notion is. It's also super helpful for when you're trying to establish trying to make up your own security notions. So let's take a step back here. We have one more step to take, which is to actually write this down as a pseudocode experiment. But I want to go back to the beginning here. So we started out with this block cipher. And we're told, okay, here's a block cipher, has k-bit keys and n-bit block size. And we asked the question, well, what does it mean for a block cipher to be secure? What's the hardest property that we want? And we decided there were probably multiple answers to this question, but that a natural one was that it should definitely be hard to recover the block cipher's secret key, because if you can recover the key, then all bets are off. And we established the fact that, well, so if the key is picked uniformly at random and the key is 128 bits long, then any attack that tries to recover the block cipher's key can win with probability at least this, because that's what you get just by guessing each bit independently and uniformly. Actually, you don't have to. You could output the all zeros as your guess, and this would still be the probability because the key itself is picked uniformly at random. So, okay, we said that that was sort of an intuitive attack, but we wanted it to be secure against adversaries that are smarter than that. So then we took the step of saying, okay, well, let's see if we can figure out like what kinds of attackers do we want to be secure against. So we came down here and we said that we want to consider adversaries that can choose potentially many plaintext values and see the resulting ciphertext pairs under some uniformly random secret key k, And the adversary's goal, the adversary's job, is to recover the key. Okay, so we got a little bit closer to a definition here. And then we took this, which is still, just a prose definition, if you will, and we turned it into this picture. And this is the typical process that we go through. You have some object. You want to know what the security property is. You start to think about, okay, what kinds of things can the adversary do? And what's the adversary's goal? Once you've written those down, then you draw yourself a picture like this one, where we formally are capturing what we've set up here. We've got an adversary that has access to E sub k, right, under a uniformly random key k. The adversary can see potentially many, can in fact choose plain texts, potentially many of them, q of them, and see the resulting ciphertext that come back under the secret key k. And at the end of that, it outputs its guess k prime, and it wins if k prime equals k, if it recovers the key. And we've said that we allow adversaries to be adaptive in that they can choose which queries to ask. And so in fact, this isn't just a chosen plaintext attack. What we've really described here is, let me just add this to the front, an adaptive chosen plaintext attack. Adaptive chosen plaintext attack, but we still just write CPA because we'll almost always assume that attacks are adaptive, so nobody actually ever writes this. Okay, well that's actually really pretty cool. We started out with this super fuzzy, English language thing of, well, I want my block cipher to be secure, and I'm going to define security to be that it's hard to recover the block cipher secret key. We took that and we turned it into something that we could really actually reason about, right? We turned it into this picture. This picture describes for us an entire probabilistic experiment. And we're going to write down explicitly what this experiment is in a minute, but you can see, I feel like maybe I'm just repeating myself now, so speed this up if this is boring. The experiment starts by picking a key k, and then the experiment is that the adversary is given oracle access to the block cipher with that secret key k. It's not given k as input, mind you. It then asks adaptive queries to this oracle, and it sees the responses, and at the end of the game it outputs k, and it wins if k equals k prime. And we'd like to now say, okay, we've been talking about the probability of winning, right? So we're saying the adversary wins if this is true. So this is some event. This guessing the key is some event. So we really would like to ask, for a given number of queries Q and a given amount of computational time that's used by A, what is the probability that the adversary wins? This is the question that we ultimately want to be able to answer. Now, before we go any farther, Q we've already talked about, right? Q is the number of oracle queries. And we've sort of intuitively said that as the number of oracle queries goes up, we expect that adversaries are going to win with probability that should increase too. It certainly can't decrease, right? Because you could have an adversary A that asks a whole bunch of oracle queries and then simply ignores them all and guesses randomly at what the key is. That adversary gets the advantage that we described earlier of 1 over the size of the key set. So you can't do any worse in terms of winning, the probability of winning the game by asking queries. You can only do better. So we expect intuitively that as you ask more, the probability of winning goes up. I haven't talked at all about the running time. So the adversary running time, we said that the adversary can ask a query and then offline do some computations to decide what the next query should be and so on. We need some way to sort of measure the running time too. And the reason that we do is because you can imagine, let's say that the adversary just asks 1 plain text and gets back 1 ciphertext. So the Q value is 1. And now the adversary spends an exponential amount of time. So what might be an exponential amount of time attack that it could use? Well, it could do what we'll call exhaustive key search. This is sort of intuitively what you you may think of as like the sort of most boneheaded attack, right? Is I ask an input, I see an output, and I know that there's some key K that describes the mapping from that input to that output. And so what do? I now sit offline, and since I know the algorithm for E, remember we always assume that attackers know the algorithm, they just don't know the key. So think that this is like AES, right? I've seen one input-output pair under AES. So what do? I sit offline and I run for something like 2 to the 128 steps, where each step is I start with the first key and I try locally on my computer to encipher under AES the value that I asked under this first key and see if it matches the value that I saw back from the oracle. If it does, I put that key aside as a potential winner. There could be more than one key that actually explains that. Remember, I said that the particular mappings that are induced by any key, they are their own things. They're not tied together. So it could be that maybe if you ask for the all zeros, that there are potentially many keys that give you a particular value out here. Well, so then what do? You just continue on. You take this value. Let's say that first key didn't match. So what do? You take the next key in lexicographic order, and you encipher under that key the value that you asked of the oracle and see if it matches the value you got back, and so on. If you run through all of the 2 to the 128 keys, well, you know one of them has to be this key that's here. So in the set of candidate keys that you've been keeping off to the side, the ones that do explain the input-output that you saw from the oracle, you know that this key is in there somewhere. And in fact, we'll be able to argue, maybe I'll do it as a homework problem, or maybe we'll do it in class, or yeah, probably in class. We'll be able to argue that in fact the size of the set of keys, the candidate keys that will explain a particular input-output pair is small. The expected size is something like 1, maybe 2. It's very small. And so this is giving us the intuition that if we allow the adversary to run for an exponential amount of time locally, then again, the probability of winning this game is going to go up. So we're going to wonder not only about the number of queries, because as the number of queries goes up, we expect that the adversary has a better probability of winning. We're also going to be concerned about running time, because if the adversary runs for an exponential amount of time, even if Q is small, we've just said that there is an attack which is very likely to win this game. So we'd like to know for a given value of Q and some amount of running time T, what's the probability that the adversary wins this game? We'll say more about running time. We'll have to make this a bit more formal later, but for right now, this is fine. Okay, so in order to be able to write down a way to measure exactly this, we need to turn this picture, we need to go the last step, which is to turn this picture into a pseudocode experiment.